Thank you so much for the introduction. So this is the last talk for today, and I would like to present about one of my work that is currently working as well, actually about a quantum error mitigation method, and titles noise-aware calibration-based adaptive gate folding for linear zero-noise extrapolation. So essentially working on the zero-noise extrapolation, or ZNE. And moving on to the introduction, as you all know, currently quantum computers has so many noise issues, and QEC is still far from reach. And according to the IBM roadmap here, we are still relying on the QEM until probably 2028. After that, hopefully we can get a QEC that can correct the logical qubit. But until QEC, there are still issues that QEC itself, like surface code, cannot correct. It essentially can correct the bit flip and phase flip, but there are some source of error like crosstalk and leakage that might turn the qubit itself into an uncomputational basis. So at that point, it's really hard to correct, and we might be able to rely on QEM at that point as well to correct that source of error. And in my talk here, I would like to focus on the zero-noise extrapolation, or ZNE error mitigation method, which was originally proposed under the reference here in physical review letters a while ago already. It is a very famous one. In the original paper, they discuss everything in detail, how the ZNE work, and noticeably, they also introduced the PEC, probabilistic error cancellation, as well. So this paper is very famous. So if you want to dive deeply into QEM, I suggest check out this paper in detail. But back to the work here, I want to talk about more of the practicality of that ZNE itself. So with ZNE, originally we have an original circuit that, for example, with this gate. And then we want to scale it further using the same gate to make it much noisier. And we call it lambda here, being the scale factor 1.5 or 2, essentially making more gate into the original quantum circuit. And then you want to apply the ZNE model to mitigate, or if you have a few data points where you would here scale from 1, 1.5, and 2, then this is the original circuit at 1 with its original noise level. And then you have at 1.5, you would scale the circuit into a little bit more noisier, essentially the same gate. And at that point, the expectation value of the circuit would drop. And then it would drop lower if you scale it into much noisier. Afterward, you would want to use ZNE, either linear model extrapolation or exponential, and some other more sophisticated like Richardson, like you can check in detail. And using those models, we can extrapolate this noisy error, filter out the error, and then you would get the expectation value closer to the ideal one, which is in this case 1. And then compare to the unmitigated result, which is the same as 1 here, we can see that we can improve the expectation value of the noisy circuit within the noisy environment. And I would like to point out that in this recent experimentation to showcase the how quantum computer can essentially find some issue or problem that is intractable by classical computer, usually they use a combination of ZNE and dynamic decoupling to mitigate the error in the quantum computer. Okay, so in this work, we discuss in detail how we fold this noise. And in the current existing folding method, we can simply use the local unitary folding. So in this folding, essentially we apply each folding operation itself to each of the quantum gates individually. For example, you have a unitary operation here, and then you simply scale it 2 more times, and the U dagger and U here simply cancelling each other out. And this is the case of folding for example 2, and then if you have 4 scale factor, you just simply scale more of the unitary operation. And this is the local unitary folding, and the other one is the global. The difference between local and global is local treating each of the gate as a unitary operation and then scale it from there. But then for the global scale folding, it treats the entire circuit as a single unitary operation, and then it mirrors that circuit. So yes, this is the most used folding, and all of this method is actually available in MITIC framework that you can test and use it. What are the limitations though into these two folding methods is that they assume uniform noise scaling. So either of the qubit, if you check on the calibration data, especially from IBM, there are some gate that has higher error rate, and there are some gate that is simply faulty gate that we cannot use it, especially for the CNOT. And within the uniform scaling assumption, it can introduce some extrapolation bias, yes, due to the imbalance noise accumulation into the quantum circuit itself. So that motivates us to propose our method is to use the real device calibration data to selectively fold the gate. Essentially, this is the entire workflow. First, we apply a noise adaptive mapping. Before we fold the gate, we first map the quantum circuit into an optimal qubit where it has lower error rate first. But then afterward, we accumulate the, we call it error rate accumulation matrix, where we compute the error rate of the entire circuit, and then we start to scale it from there. To see everything in detail, first about the noise adaptive mapping, we can see that the quantum circuit is first calculated on how each error rate is affecting this entire circuit based on the calibration data that we got from here. This is the matrix showing the two gate error rate. In here we ignore the one gate error rate first, but essentially it works in the same way. Okay, so after accumulating, we can see that the red point here, I'm sorry, it's a bit small, but the red point here essentially has higher error rate than the blue one. So if we were to scale, we want to limit the scaling on the red point already because it has severely high error rate, so we want to limit that. Then at the accumulation point is just analyzes the quantum circuit itself and then collect all of this data. Afterward, the most important point is to calibration guided selective folding. So essentially, we want to fold the gate differently from the one that we have lower error rate. So I think the full picture will show more. At this point, we can see we have more gates on this part than the other one, because the blue one here, I'm sorry, I was confusing. The blue one has higher error rate than the red one. So in this folding, we fold the red one more aggressively than the blue one in our method. Okay, so this is essentially all of the entire method. You can check the paper for more detail on how it works and why. But I want to show more about the result in our experiment. We select two circuits for our experiment. The first one is this circuit, which is very easy to execute because the connection between each CNOT gate can essentially connect on all of the qubits that have adjacency connected to each other. So this circuit requires essentially no swap gate on most of the quantum computer. And we scale from, I believe, 27 qubit to for this execution. And then the other circuit we select is this BV circuit at about 14 qubit to show the practicality as well. And to our comparison target, we focus on the local folding and the global folding like I've shown you. And the implementation that we use is from MITIC library or framework. Also, we use the linear extrapolation model to calculate or extrapolate the error from all of the folding methods in here equally. And this is the result. On the left Yes, on A here, it is a simulation result using the noise model from the real device, which is IBM Cube here. And this B side is the real hardware result executing using the same setup and method. As you can see on the simulator side, we can execute up to 18 qubits of the configuration on the circuit A a moment ago. And we can see that the mitigated result of the noise aware folding, starting from about 6-7 qubits, we can see it spikes up and the expectation value at that point improves as well compared to other. And then in some cases, noticeably around here, the mitigated for global and local folding actually much worse than the unmitigated result at this point. And for the real hardware, as you can see, actually the expectation value starting from 4 qubit point, it drops significantly compared to the simulator, because assumption on the real hardware, it is much harder to execute such circuit, and also as the depth increase, it also accumulates the error differently than the simulator. The simulator only using some error rate that is available on the calibration data, like decoherent gate errors and so on. So it is more okay to execute the circuit at a higher depth. But then on the real hardware, we can see the expectation value drops significantly starting from 6-7 qubit. That is the execution result on real quantum computer. And this is the recent data as well that we execute just for this conference. And for this one, is actually the execution from a while ago using the noisy simulator with the noise model from IBM Q Mumbai, executing for the PV circuit at 14 qubit configuration. And as you can see in here, I put on all of the scale factor expectation value in each of the folding. You can see that on the noise aware folding, the expectation value dropped like as expected for the noise scaling. Yes. So then in the extrapolated result, we can also see it is closer to the ideal value that we expected from the quantum circuit. Okay, so that is the result, and I would like to conclude our work and also future work as well. In essence, we propose a noise-aware folding method for the Z&E error mitigation method using the real-time calibration data from the real quantum computer, and we achieve about a 22 and 26 improvement over simulator and real quantum computer respectively. But I think there are a lot of things that can be improved in terms of this noise-aware folding or folding in general for Z&E. The first thing is that because we fold the quantum circuit and then adding the gate sequentially, there are some qubits that is idling for a very long time. And during that idling process, the decoherent will kick in much quicker. And at that point, implementing or cooperating it with the dynamic decoupling would essentially improve the success rate of your circuit within the execution. And in here, I propose about the gate level folding. So if we want to dive deeper, maybe we can consider about the pulse shaping level as well. At that point, we have a higher control over how we want to fold the gate pulse sequence and address much better where does the noise occur. And also, this one is just full application benchmark. We want, in my research, I want to focus on more of the quantum machine learning algorithm as well. Yes. So that is all for today. Thank you.
Thank you very much, Leanghok, for this very great last talk. So there we have some questions, please. Yes.
Thank you for the talk. The examples you showed were quite specific to the way that superconducting architectures work. Do you see ways to generalize this to other architectures where qubits might be mobile or other variations from IBM system?
Thank you so much for the question. So in the example here, as you mentioned, specifically for the superconducting computer, but in theory, it should be work on all type of quantum computer, especially the gate-based quantum computer. But I haven't tested on some other platform yet because of it's hard to reach to those platforms for the execution. Yes.
So there's a pretty strong drop in the real device, and the method still quite works very well. I think you probably mentioned why. Could you explain that again? What do you think? What happens there?
Okay, so the big drop here, essentially, I was using on the IBM Cube here, the decoherence on that is very, very low. Co-coherent and decoherent, the T1, T2 result is very, very low. So as the number of qubit goes on, if we look at the circuit again, the depth would increase as well. So at that point, for this device specifically, we was using the fixed coupler, and the decoherence is very low. And I think it is the biggest problem regarding to this dropping for the expectation value.
I mean, is the circuit then shorter for the mitigated?
No, the circuit grow longer during the mitigation process.
Yes. No, because the results are, the expectation value is still pretty high then comparatively, right?
Yes, because at this point we can still get some meaningful results from the real quantum computer. So at that point we can still mitigate and fix some of the error. But at higher level, at 9 or 10 afterward, the result just almost completely random.
Yeah.
Yes, right.
Yeah, that's right. Yeah.
Thank you.
Yeah. More questions? Okay, let's thank you again.